All right, so this video is going to cover some examples for determining integrals of concavity. So we're in section 3.4, and so before I go into the examples, just a quick recap. Concavity refers to the shape of the graph in the sense of, is the graph opening up or opening down? And so here's a picture I drew. The function's in green, and notice I have in purple, it says concave down. The graph's opening down for that portion, and its second derivative is less than 0, which means second derivative is negative. And the other portion I have written in orange that it's concave up, so it's opening upward, and its second derivative is greater than 0, so second derivative is positive. And then in yellow, I have x star. And x star is an inflection point. And that's the point in which the graph switches from concave down to concave up. And for the inflection point, its second derivative is equal to 0, or the second derivative does not exist at x star. All right, so this is concepts discussed in the previous video. It's, I think, important to know as far as when we determine intervals of concavity. So the strategy in which we're going to find concavity, intervals of concavity. Well, the first thing I'm going to do is find the first and second derivatives. And then after I find those two derivatives, I'm going to find the potential inflection points. All right, because if I know the potential inflection points, then I can, from there, create the intervals. And based on the intervals, I'll pick a test value from each one and determine, is it concave up or down, depending on if its second derivative is positive or negative. So here's the strategy if you want to pause the video and write this down. So there's essentially 4 steps. I kind of already said them, but first step, first, second derivative. Second step, you find the potential inflection points, and you do that by setting the second derivative equal to 0, solving for x. The third step is you're going to form the intervals, and then you're going to pick test values from each interval. Fourth step, you're going to plug each test value into the second derivative and make note of the sign. So if the second derivative is positive for that test value, then the graph's concave up. So the graph is opening up. And then if the second derivative is negative for the test value, it's going to be concave down. And if it's 0 for the second derivative for the test value, that means the graph of the function is linear. So you have like a line. All right, so pause the video, write down those steps, and now I'm going to apply this strategy to the problems. So here are 2 examples from the textbook. We're going to determine the open intervals of concavity. And I'm going to do it out of order. I'll do number 7 first and then number 5. All right, so the first thing I need to do is, well, I need to find the first and second derivatives. So the first derivative, f prime of x, so I just normally just take the derivative of f of x, so I use the power rule. X to the 4th becomes 4x cubed based on the power rule, and then I have minus 3 times, and I do the power rule with x cubed. Well, the power rule with x cubed, that's going to be 3x squared. So it's the first derivative is 4x cubed minus 9x squared. All right, so that's the first derivative. Now here we're going to find the second derivative. And the second derivative is the derivative of the first derivative. And I'll even put it in a different color. So we denote the second derivative as f double prime x. So I'm taking the derivative of the first derivative. So 4x cubed, that becomes 4 times, and then the derivative of x cubed is 3x squared. And then minus 9 times the derivative of x squared, that becomes 2x. So the second derivative is 12x squared minus 18x. All right, so that's the second derivative. So we've done step 1. Now I'm going to find any potential inflection points by setting the second derivative equal to 0. So now find any inflection points. And so I set f double prime of x equal to 0. So I'm going to set 12x squared minus 18x equal to 0. And solve for x. And I would try to do some factoring. And as far as the factoring goes, I can factor out 6x. So that will give me 2x minus 3 equal to 0. And then I have 2 factors. So one of them is 6x. I set 6x equal to 0, and you divide by 6. That gives you 0. The second one is 2x minus 3 equal to 0. You add 3 to both sides and divide by 2. So you get 0 and 3/2 are the 2 potential inflection points. All right, and I'll go ahead and just circle those so that we have all the important stuff. So we have those 2 potential inflection points. This is the second derivative. I'll be using that. I'm going to go back to the color blue. All right, so that's the second step. Now I need to form the intervals and then pick a test value from each interval. So I just form a number line. So we have 0 and then 3/2. So the intervals so I have the portion that goes from -infinity to 0. So that's one of my potential intervals. Or sorry, actual interval, but from based on the potential inflection point. Then I have in between 0 and 3/2. And then the third interval, 3/2 to positive infinity. And so I pick a test value from each interval. So for the first interval, I'll pick a test value and I'll use don't know, let's just use a different color. So I'll use x1. From this interval, I'll use -1 as my test value. All right, the second interval, I'll just choose 1. And then I'll choose 2 from the third interval. Those are my test values. Now I just plug in each test value into the second derivative. All right, and the second derivative we found was 12x squared minus 18x. All right, so for the first one, first test value, that's going to be f double prime of -1. That's going to equal 12 times -1 squared minus 18 times -1. And we only care about the sign. So when you plug this in, so that's going to make this 12 times 1 is 12, and then 12 plus 18, because of the double negative makes that positive 18. So that's going to be 30, which is positive. All right, so when it's positive, that means it's concave up. All right, and that's concave up for the test value -1. -1 came from the interval -infinity to 0. So it's concave up on that interval. All right, so that's part of the answer. Now you just do the same process for the other ones. So if I did the next one's 1. All right, so that's going to be 12 minus 18, which gives you -6. We don't care about the actual value, just the sign, so it's negative. So that means the graph is going to be opening down. So negative is concave down. And that was for the second interval, because their test value 1 came from the interval from 0 to 3/2. So it's concave down on 0 to 3/2. All right, so our last value I chose was 2. Okay, so when you plug in 2, this comes out to be 12. So that's positive. So concave up. And that was the last interval from 3/2 to positive infinity. All right, so that's our answer. It's just the intervals of concavity. It's very similar to the first, well, finding intervals of increase and decrease from previous section. So we first found first derivative, second derivative. From the second derivative, I find any potential inflection points. And recall our inflection points when the graph's going to shift concavity. So we found the inflection points by setting the second derivative equal to 0, and I got 0 3/2. From those two values, I formed the intervals. And I have three intervals: negative infinity to 0, 0 to 3/2, and 3/2 to positive infinity. I pick three values from each interval, or I'll pick a value from each interval. It makes three values total. And these are just up to my choice. So I picked -1, 1, and 2. Seemed pretty easy values to plug into the second derivative. And then from there, I plugged it in and determined what the sign was. If it's positive, that means it's concave up. And then negative for the second derivative means it's concave down. So that's the process we go through to get the intervals of concavity. Now the next one is number 5. So it's x squared minus 4x plus 8. So again, find both derivatives. So the first derivative, f prime of x, derivative of x squared is 2x, and then minus 4 times 1, because the derivative of x is 1, and then plus 0, because 8 is a constant. So the first derivative is 2x minus 4. Then I find the derivative of the first derivative to get the second derivative. So f double prime of x. So derivative of 2x is 2 times 1, and then plus 0 because derivative of constant 0. So the second derivative is 2. Now notice here I get a constant. So note, here we get f double prime of x being a constant value. This means no matter what x I plug in, you always get 2 for the output. So since 2 is positive, so in other words, the second derivative is greater than 0 always, then the graph is concave up everywhere. All right, so this one, the answer is just concave up from negative infinity to positive infinity. So there's no inflection points, in other words. Again, so we find first derivative, came out to be 2x minus 4. The second derivative is the derivative of 2x minus 4, which is 2. So that's telling us that no matter what x value you plug into the second derivative, you always get 2 for its output. And since 2 is positive, that means the second derivative is always going to be positive for any x. So that means since it's positive, that means the graph is opening up. So it's concave up everywhere. And so you would say concave up, negative infinity to positive infinity. All right, so that's the answer for that one. Now, one thing to note is that this is a quadratic function. Quadratic functions have the structure ax squared plus bx plus c, and the graph of these is a parabola. All right, so for the graph of the parabola, it's either going to be opening up or opening down. All right, that's just added information. Figured that makes sense of that. So we have a quadratic function, which basically means we have a parabola. And the parabola is either going to open up or down. And in this case, it opens up. So that's another interpretation of how we get the concave up, or negative infinity to positive infinity. All right, so that's where I'll stop it for this video. The next video is going to be determining inflection points.